In this video, I will show you a couple basic examples of analyzing an ideal op-amp circuit. If you haven't seen my video on ideal op-amp assumptions, go watch it now. I've put a link in the video description. You need to see that so that you can know how to begin analyzing this. So we never have an op-amp just by itself. It's usually built into a circuit so that we can do something, so we can process a signal. Maybe we're going to amplify it, or we're going to take the difference between two signals, or add two signals, or even integrate or multiply signals. So this is a very basic op-amp circuit, and we have one voltage source. We're generally looking for the output voltage, or we might design the op-amp for a specific output voltage. The general approach to this is first to apply the ideal op-amp assumptions. And the two implications of the assumptions that I identified in the last video are that the input currents to the op-amp are zero. That's because the op-amp has infinite input impedance. And then a consequence of infinite gain is the fact that the two input voltages have to be the same. One thing that's instrumental in an op-amp circuit is this RF. This allows the op-amp to create whatever conditions it needs to establish the ideal op-amp. So its output creates the necessary current to make the two inputs the same voltage. So that feedback resistor is very important. So we'll first apply the ideal op-amp assumptions, and then we'll use circuit analysis to design the circuit or solve for the output. Okay, so we'll apply our assumptions. We'll start off with the assumption that the input current is zero. So there are two of them. And we recognize that V minus equals A volts. And we recognize that V minus equals VA. That also then tells us that V plus equals VA. So we've now used this op-amp assumption. Now let's use the other op-amp assumption. Well, 0 amps flowing into the op-amp means that there's 0 amps flowing across this resistor. And that means that the voltage drop in this direction is 0 volts. I could reverse the direction and the voltage drop would be the same. So that tells us then that V out is also VA, right? Because there's 0 voltage drop across that feedback resistor. So this may not seem like a very useful circuit. It just makes VO be VA, but this can actually be useful. What the op-amp does is it isolates the input from the output. So like changes on the output will not affect the input voltage. The operating amplifier adjusts the output current as needed to maintain the proper output voltage. So a device that takes an input voltage and makes the output match the input is generally what we call a buffer. So that's very nice in circuits and machinery where you don't want to affect upstream voltages from a downstream voltage. So that's fairly simple and straightforward. Here's a more involved example. I'm just going to get my steps here from above. We'll paste them down below. Okay, so here we will apply our op-amp assumptions. So we know that this is 0 amps, and we know that this is 0 amps. Because we know that that's 0 amps, we know that this voltage here, V plus, is equal to VA. How did I know that? Well, that's because it's a 0 volt drop across here, so it has to be the same voltage on either side of the resistor. Because we know that's VA, well, we have a virtual short between these two nodes here. Virtual short, so this also is VA. So now we've applied that assumption, and we've applied I plus equals I minus equals 0. So we've applied our op-amp assumptions. Now we'll use circuit analysis. And one thing that is very common in these problems is that you want to write a KCL equation at the terminal where the feedback connects. So where is that? That's here. This is the input terminal where the feedback resistor connects. So we're going to do KCL here. All right, so what do we have? We have VA minus VO over RF. That's one current leaving. Another current leaving that node is VA minus VB over RB. And then the last current leaving is 0. That's the one going into the op amp, the minus terminal, inverting terminal. All that's equal to 0. Now we will push VO to the other side because we're interested in solving for VO. And then finally we multiply everything by RF, and then we'll group things in terms of VA and VB. So the first term gets us a 1. The second term, when we multiply by RF, gives us RF over RB. And then for VB, looks like we just have a negative RF over RB. Again, we multiplied both sides by RF, so we just have VO here. So now we know what VO looks like, and we should be satisfied because we see here that VA and VB, well, we know those have units of volts, and then these coefficients are resistors over resistors, so that's unitless. So our answer has units of volts, and that's good. The other thing we can do is write this like this, VA, and it has some gain A, gain B, times voltage B, VO. And we can recognize that voltage A has gain AA, which is this. AB, gain B, is just negative. So what does this op amp do? Notice it performs basically a weighted subtraction between VA and VB. So it takes a difference, and that difference, well, it's VA and VB are inputs, and they get weighted by AA and AB. And depending on how you want to weight the two terms, you can design these gains AA and AB. So we see that gain A is always greater than 1 because resistors always have positive values. So that means that this is an amplifying portion of the circuit. And then AB or gain B is less than 0. So this inverts signal B. We don't know yet whether AB amplifies or attenuates. You can design gain B for amplification, attenuation, or even just buffering, unit gain. So that's kind of nice. We can design the gains, AA and AB, and then we perform a weighted subtraction because gain B is an inversion. So we can sort of design this to implement a weighted subtraction.